kind introduction, and also many thanks for the opportunity to give this talk and to be at this very nice place. So what I'm going to talk about is some joint work in progress with Daniel Hug and Günter from Karlsruhe. The idea of this project is that the Boolean model is a classical topic from stochastic geometry, but usually it is studied in Euclidean space, whereas we will study it in hyperbolic space. And so one of the main points of my talk will be to compare what we observe in hyperbolic space compared to Euclidean space. So let me start my talk with some facts about hyperbolic geometry. So let us start with the picture here. Whenever I show you pictures, I use Poincaré disk model of hyperbolic space. So the Poincaré disk model is a two-dimensional model, so it's for two-dimensional hyperbolic space, but there's a more general Poincaré ball model. And in the Poincaré disk model, hyperbolic space is here this black circle. And what you can see here are here's a geodesic between these 2 points. In case of 2 antipodal points, the geodesic goes through the center of the disk. Moreover, you can see here two-dimensional hyperbolic boards, which are again circles in the Poincaré disk model, but you must be careful since the hyperbolic center is not the usual center of the circle. So what is important to note is that there are different models for hyperbolic space, but it does not matter which model you take for our result. So this is independent of the model. So I denote by HD the d-dimensional hyperbolic space. And within this space, we denote by KD the set of compact convex subsets. In this talk, we use isometries on hyperbolic space, and the set of all isometries is denoted by ID. And then we can equip the set of isometries by a Haar measure, which we denote by lambda. For this Haar measure, we can just choose the normalization, and we do it such that this equation here holds. So the idea here is the following. We take a fixed point of hyperbolic space, and then if we integrate here over all isometries that move our fixed point x to some given set, this integral is exactly the Hausdorff measure of the set. Then, throughout this talk, we study voids in hyperbolic space. And so we choose P as a fixed point. You can think of it as a counterpart to the origin in Euclidean space. And then ER is a closed ball with radius R and center P. For what we will observe in this talk, the following formulas are very essential. So here we have the surface area and the volume of a ball with radius R in hyperbolic space. And we are interested in the asymptotic behavior as R goes to infinity. What you can see here is that for R going to infinity, the order of the surface area and the volume are the same, and this will be essential later. Okay, now we are ready for introducing our Boolean model. So what we take is a Poisson process eta on KD. So this means that the points of eta are compact convex sets, which we referred to as particles. So here you can see a realization. So the circles here are our particles. So what I did here is that I said that the particles are balls with random radii. So in the picture you must observe that in the Poincaré disk model, circles further away from the center look smaller. So these small circles here close to the boundary are not necessarily smaller than those to the center. That's just a feature of the Poincaré disk model. For our underlying Poisson process, we assume that it is stationary, and this means that its intensity measure lambda is invariant under all isometries. Okay, now we take the union of all our particles, which gives us a random closed set, which we call Boolean model. So later I will compare our results with those for the Euclidean situation, and it should be for all of you who are not familiar with the Boolean model in the Euclidean case clear what we do. We do exactly the same, but we just take a stationary Poisson process on a set of compact convex subsets of RD, and this gives you the Euclidean Boolean model. In this talk, we consider our Boolean model just within some compact convex observation window, and usually our observation window is a ball of radius r, and we are interested in the case that our observation window is increased, meaning that we let r go to infinity. And then we are interested in questions like how much of our observation window is covered by the Boolean model. There's one more technical assumption which we need, namely we have to assume that our underlying Poisson process is locally finite, and this just means that for every compact subset C of our hyperbolic space, the expected number of particles hitting C is finite. And if this assumption is satisfied, we have some alternative representation for our intensity measure lambda, which you can see here. Namely, there exists a probability measure Q, such that we have here this identity. And the idea here is the following. So instead of integrating with respect to lambda, you can do the following. You take some compact convex set distributed according to the probability measure Q, and then you move this fixed set around with isometries, and here you integrate the isometries with respect to your R measure, and then here is some intensity parameter gamma. Moreover, this probability measure Q here has a property that it is invariant under all isometries, keeping our point P fixed. Now we use this measure Q to introduce the so-called typical particle, which is just a random compact convex set distributed according to Q. And now, if this assumption here is satisfied, then we know the following, namely that G1, which is the one parallel set of our typical particle G, that this has a volume with a finite expectation. Throughout this talk, we will often state assumptions in terms of the volume of the one parallel set of the typical particle. So, to present our main results, we need one more concept from hyperbolic geometry, namely so-called horoboids. And in order to help you to better understand this, let us just start with Euclidean geometry. So what we do here is that we have our origin, and then we have here a fixed green point, and then we take a circle having the green point on its boundary. What we do now is that we shift the center of the circle further to the right and more further to the right, and then if we take the limit of all these voids, we obtain just the half space that is delimited by the red line here. Okay, now let us try to do the same in hyperbolic space. So we start here with the same situation, and then we move the center further away from the origin here to the right, and we go on with this, and then again we get some limiting object, and this limiting object is called a horoboid. And now it is very important to understand that this is something different than a half space, because the half space would be now everything to the right of this line here. So in other words, you can think of horoboids as the limiting object of a family of boids, which does not exist in that way in Euclidean space. So it's something completely new to hyperbolic space. So for horoboids, we use the following notation. So BUT stands for the horoboid if the centers are here in direction U, and if this green point here has a distance t in direction U to point P.
And the direction is the direction tangent space?
Yes, yes. Now we are ready for the first result. So we denote by V1 just the expected volume of the typical particle. Moreover, we introduce here the so-called covariogram of the typical grain. It's a function depending on 2 points x and z. And what we do here is that we consider the set of all isometries that move x and z to our typical grain, takes the Haar measure of these isometries, and then the expectation. Now we can show the following. So we intersect our Boolean model with some observation window and take the expectation of this volume, and the expectation is now the volume of the observation window multiplied by this formula, this expression here, and this is just the probability that the fixed point is covered by our Boolean model. So this formula here looks exactly as we know it from the Euclidean case. So now let us move on to variances. And what we do here is that from now on, our observation window is always a ball of radius r. So we take the volume of the intersection of the Boolean model with the ball of radius r, take the variance and rescale here by the volume of the observation window. And then we can prove that the limit is given by this expression here. So we have here a first term involving the covariogram of the typical grain, and then we multiply here with the probability that the point that we integrate over belongs to some random horoboid. So this formula here is now different from what we know from the Euclidean case. And so let me show you the comparison. So here on the left-hand side, you have the formula for the asymptotic variance of the volume in the Euclidean case, and here in the hyperbolic case. So you see that the first factor is the same, and then this term here and here is also the same, but what is really new in the hyperbolic case is this probability involving the random parabol, which is not present in the Euclidean case. Okay, so what we see is that this additional factor here emerges. And now let me try to give you a brief explanation why we get this probability here. The reason is that this additional probability comes from boundary effects. So let us start first with the Euclidean case. And here we are interested in the intensity measure of all particles intersecting the boundary of our observation window. Now one can show that this behaves as the surface area of our observation window, which is given here. And now we compare this with the volume of our observation window, and then you see that the order here is smaller than the order of the volume of the observation window, and therefore we can, for asymptotic analysis, neglect the contribution from points intersecting the boundary. Now let us do exactly the same for hyperbolic space, and here we have the order of the intensity measure of the particles hitting the boundary, and we see that it is of the same order as the volume of the observation window, and this means that we cannot neglect the effect of particles intersecting the boundary, and so this factor here comes from the contribution of the particles intersecting the boundary of the observation window. So the difference we observe here between Euclidean and hyperbolic space is that in hyperbolic space we have more boundary, and therefore we have more particles that intersect the boundary, and their contribution leads to this term here. So our results are beyond volume. We can study more general functionals. So we denote by RD the convex ring, which is a set of all finite unions of convex sets. Now we say that a functional on the convex ring is geometric if it satisfies some assumptions. So phi needs to be measurable and additive. Additive just means that it's a valuation. Then we assume isometry, invariance, and finally local boundedness. And this means that the absolute value of phi of all compact convex sets that are contained within some ball of radius 1 are uniformly bounded. For some of our findings, we additionally need to assume that phi is continuous on KD. To formulate our general results, we also need some measure HD as a set of all parabols, which is introduced here. Okay, now we do the following. We take a geometric functional, which we assume to be continuous on KD. We take the expectation of phi of the intersection of the Boolean model with a ball of radius r, and divide here by the volume of the observation window. And then as r goes to infinity, we obtain as a limit this expression here. And so what we have here are intersections of the typical crane with, of the typical particle with further particles, as well as a horror ball here, and we integrate here with respect to measure introduced here, our intensity measure, and the probability measure of the typical particle. Instead of the expectation here, we can also derive a formula if we take here the variance, and the structure is similarly as for the expectation. Now the interesting question is, how do these formulas differ from what we know for the Euclidean case? And there are two differences. The first thing is that here and in the previous formula we integrate over all horoboids, and in the Euclidean case you do not have this integration. And the second difference is that here we need to assume continuity of phi, which is not necessary in the Euclidean case. And here both these differences again come from our boundary effects. So the horoboids come from the boundary effect, and in order to be able to control what happens close to the boundary, we also need here continuity. So what we were also able to derive are central limit theorems. So here we study geometric functional, and we assume that the variance of phi of the intersection of the Boolean model with the observation window is bounded from below. What we need to assume here is that the second moment of the volume of the one parallel set of the typical particle is finite. Then we can take here phi of the intersection of the Boolean model with the observation window and standardize it. And as the radius of BR goes to infinity, we obtain convergence and distribution with standard Gaussian random variable. In case that we assume here fourth finite moment instead of a second finite moment, then we can even provide a rate of convergence for this convergence distribution here, which is 1 over the square root of the volume of the observation window. So here we have this assumption, which basically means that the asymptotic variance is not degenerate. And in order to check this condition, we also have a theorem. And this theorem tells us that this condition here is satisfied if we can verify such a condition here. So we take here a typical particle and m further particles according to lambda, and if we can somehow show that phi of their intersection does not vanish too often, then we can prove that this expression here must be positive. So let me use the last slide to say a few words about our proof strategies. So the first thing is that the overall ideas are similar to those used in the Euclidean case, but what is crucial is that one needs a more careful analysis of boundary effects, which lead to the emergence of the horoboids in our formulas. Then central limit theorems can be shown by applying second order Poincaré inequalities as in the Euclidean case. And then let me show you some further ingredient for our proofs. So in order to prove the previous theorem here, we use some general result for Poisson functionals, which is from some joint work by Vanessa Trapp, who's in the audience, and myself. And this is a statement coding for general Poisson functionals, so it's not linked to hyperbolic space. And what one does here is to consider the first and the second order difference operator. So for Poisson functions, these operators measure the effect of adding up to 2 additional points. And then if one can establish this inequality here, where one bounds the expectation of the integral over the squared second difference operator in terms of the expectation of the integral over the squared difference operator, then one has here this lower bound for the variance. And I think that this is a very useful device which can be applied to many other problems as well. Okay, this was all I wanted to tell you, and so thank you very much for your attention.